So the next speaker is our colleague Sergey Tikhomirov. He is from the Department of Mathematics, and he will speak about traveling waves and gravitational fingers in unstable displacement in porous media.
Thank you very much. Yes, I'm from here, but I'm new here, I think less than 2 months. Yes, and partially the goal of this talk for me is just to present myself to everybody, to get know that I'm here and what I'm doing. So I'm going to speak about quite diverse topics, so it is quite a long title, because it actually comes via several subjects. I would say that it comes from petroleum engineering and applied part of it via numerical simulations to the theoretical PDs, yes, with a traveling wave included there. And I mentioned roughly 4 topics during what I'm saying, and I'm going on purpose touch each of those topics just to present myself that I am in, and I hope this is also very well, but not going much deeper inside, because it's not possible to go into 4 topics deep inside. And I hope this is well elongated with the idea of this conference. Thank you for Rodrigo. So I'm going to speak about, because this is a series of works, it was originated in St. Petersburg in collaboration with real petroleum companies. Now kind of research is a bit more theoretical, and it is a joint works with Yulia Petrova, who is also a professor here, and Yalchin Yefendiev from Texas A&M. So I would start for a while with the petroleum motivation. I say what problems inside I am solving, and and end with certain idea which I called intermediate concentration, which needs justification. This is when, before you proceed in applied side, you need to be more sure that what you are speaking about is really correct. And at that moment, it would start a theoretical part, and it's a bit, there would be a transition, because I start with viscous liquids, water inside polymer, but theoretical part would be about gravitational story. So that's the phenomena mathematically is quite similar. Okay, theoretical work is on a simpler subject. So what is happening? What is the applied context? 1 minute introduction to the oil extraction theory. Yes, so if you want to extract oil, you not just drill a well and you have oil. Yes, you on an oversimplified situation, you drill 2 wells. In one, you inject something, from other, you get something, and your goal is to inject as cheap liquid as possible and get as expensive liquid as possible. Perfect world, you inject water and you get or CO2 or gas, and you get oil outside. This is a perfect world. Not all world is so perfect. Yes, sometimes in order to get more oil, people use so-called enhanced oil recovery methods. I would speak today only about chemical enhanced oil recovery methods, but in the very, very last slide, after all my theory, I will say what other story can be useful here. And in that case, you inject chemicals, and chemicals are very similar to what you clean your dishes. Yes, so you want to clean porous media from the oil, and oil is mobilized and moves. But okay, you cannot always inject those chemicals because they are very expensive, and then it would be not reasonable idea. So you for a while inject chemicals, and after this you start to inject water. And I oversimplify, there are a lot of stories. What is important for today is that those chemicals have physical property of viscosity. So you inject viscous liquids inside. I'm not entering the chemistry part. It's not a subject today, yes? And then you see the following. You have And viscosity comes from polymer solution. Polymer is a chemical which is miscible with water. And this is important for today. So you inject polymer, and in the end you inject water. Yes? And the polymer is more viscous usually than oil and everything else. So when you inject it, it's very nice. Yes, but when you start to inject water, because it's less viscous, it starts to be unstable displacement. You see those crazy patterns. And here there are good news and bad news. The good news is the fact that you have crazy patterns is not actually a problem. You don't need this regular story. But the bad news that if you have a breakthrough, yeah, so you inject your chemicals, and after a while your water go via the chemicals and go to the forward part, this damages the process. And for this talk, this is axiom. Yeah, so that's how to say why it is like this. So you are not kind of necessarily avoid these structures at all, but you need to be these structures relatively small. This is what is your goal. One more good news and one more bad news. A good news is that you look onto those structures, and even they look chaotic. It happens that the tip, the fastest finger, moves with a constant speed. So it happens that here, that's if you look on all those chaotic structures and look on the tip of the finger, it moves with a constant velocity. This is good news. The bad news that actually nobody knows what is this velocity up to now. Yes, so that's, and more or less the philosophy of the talk is just to understand what is the velocity of this finger and what are the mechanisms beyond how we can get it. Yes, and what is happening here mathematically? Yes, so kind of I quite quickly step into mathematical part. So mathematically, it's so-called Pisman model, and this is a miscible displacement of viscous liquids because, okay, I'm on this back side. Their oil is already not moving. Actually, all the oil is moved on a front here, and then actually it's become one-phase displacement. Effectively, you have polymer and water. And C here is concentration of polymer, and we have transport in question, incompressibility condition, and porous media enters. This is Darcy law. So the velocity depends on the pressure, not like Navier-Stokes, but just velocity is proportional to the gradient of pressure, and coefficient of proportionality is 1 over viscosity. And viscosity depends on the concentration of polymer. So this is what is inside. So this is the model, and this is what's drives this picture. And intuitive idea is natural. If you have something less viscous, it's more easily goes, and then it should form such patterns. The most famous is Helly-Shaw experiment. It's a very related set of equations, but not exactly this one. There it is a free boundary. Here I don't have a free boundary. Yes, so this is a story. For me, it would be important one simplification which comes independently from the people who study this equation on theoretical side and those who are studying petroleum engineering. So in both, it is a valid simplification. Idea is the following. So here I have a rectangle. Yes. How rectangle is related to oil industry. You should think this rectangle, it is a horizontal rectangle, so there is no vertical coordinate in it. It is xy. And oil field is very thin. Z coordinate is small. And then you say, but when I drill the well, it should be a point and I should have something circular, radial geometry. Not necessary. So now people drill the so-called horizontal wells, and in that case, inside the oil field, you have two parallel lines, and you inject from one of the parallel lines, and you produce from other parallel lines. And this is geometry, of course, is a simplification, but this is not oversimplification. here. And what is assumed that the pressure mostly depends on a distance to the well rather than on a point inside. Of course, the pressure is function of two variables, but it mostly depends on x coordinate rather than in y coordinate. This is assumption, and this is confirmed by oil fields, and this is how people come in mathematics as well. And in that case, you partially can resolve the last equation, you can eliminate the pressure from the system, and but then appears asymmetry between x and y coordinates. You say that you have a velocity x and y, and you can resolve what is the value of x velocity as a certain non-local equation. You look on the vertical line and you calculate the average value of mobility 1 over viscosity, and you just have explicit formula via mobility and average mobility. So it becomes non-local problem but without pressure. And this model would play a big role in what I'm going to speak further. The idea here is that if we would like to get an estimate for the speed of the finger, so here I speak about works of Felix Otte and Govend Menon on an abstract mathematical setting, and Jorstes and Salin who put it into oil context. So let us try to estimate. I would not give the full proof, but I give the idea. The idea, because my goal is to say the list of ideas, yes, that we have this two-dimensional equation, and we have a certain estimate on the horizontal velocity. It's very easily because average mobility is at least minimal mobility and at most maximal mobility. You write these equations, you substitute into this equation in a one-dimensional setting. So you write two one-dimensional equations, and it happens that it satisfies the maximum principle between two-dimensional and one-dimensional. So if an initial data of two-dimensional is pointwise smaller than initial data of one-dimensional, then the full solution of two-dimensional system is less than full solution of one-dimensional system. And this is a theorem, this is a mathematical statement, it's not a heuristic anymore. And then after this you look on those equations, one-dimensional, it happens that they're Burger's type equation, you know everything about them, and blah blah blah, and you are able to get estimates. Okay, I wrote here qualities, this is a mistake, I need to say inequality. Yes, so the maximum velocity of a finger is not less than certain quantity. And people from oil industry it's not a sharp estimate. So when you give exactly this formula, they substitute in their process and they say, guys, you want us to spend too much money, yes, on chemicals. But what they like is that because this formula depends on the whole curve of viscosity. So here it's mobility, but this is one viscosity. So that it depends not only on a minimal and maximal viscosity, because actually the true models which they have inside, I don't know, packages to do this, they are always based on the two critical points, minimal and maximum. And this one depends on the whole curve. So they say, okay, might be you can improve, yes, stories. Because they know from practice that it depends on the curve, not only on the points. And so our question is that, can we improve this? Now start the speculative part for a while. And speculative part, so this is a theorem, Otte, Menon, Jorstes, Salin, but let us see when the theorem should provide us a sharp estimate, so when it doesn't lose anything on the process of deduction. So here is inequality, sorry. And it happens that it assumes informally that on the tip of a finger you have a constant, if here is concentration 1, then on tip of a finger concentration 0. That's included in the the estimates. And the second thing, they completely ignore existence of transverse flux on the tip of a finger. Yes, and it should be, because here you have a viscous liquid, so it slowly moves. Here you have water, so it fast moves in horizontal direction. And then incompressibility conditions tells that it should be flux in y coordinate as well. But inside the proof, it is ignored, basically. And it should slow down, yes, because if it goes to the left and to the right, then it doesn't go forward, yes. So it's not there. And what we did a careful numerical simulations of this problem, of those questions. And what we observed that if you do there and look on the fastest finger and look on the tip of this finger, and here we draw a line and the graph of the concentration along this line, because the finger, I mean, it's chaotic, yes, it's on a perfect picture. You have the finger moving forward. Yes, it's not exactly forward. You see that the concentration drops not from 1 to 0, but from 1 to a certain value. And okay, we have diffusion in a system, so there is no contradiction. But it seems that this is an effect more robust than just diffusion gives to you. Yes, because diffusion gives you actually this as a smooth transition, not this fact. Yes, so those who study travel in waves, yes, still think that it should go to 0. And okay, we observed this and we investigated this a bit more, and we assumed that, okay, assume that we have this intermediate concentration as a pre-known. And can we repeat Otto-Menon approach? And yes, we can, and we will get other formula. I mean, I'm not asking, too much ideas of it. It's still based on this comparison with one-dimensional with another one-dimensional. But what is interesting that if you look onto this quantity, it is damn good coincide with the velocity of the finger. We have this as a theorem, we call it a posteriori estimate, kind of if you made a simulation where you observe on the tip of a finger such type of drop, not to 0, then we can prove a posteriori that the velocity is not higher than this value. I don't put exact statement of the theorem because what is finger is not so easy to determine theoretically. It's very easy visually, but not as a mathematical statement. So, but I have extra slides. Yes, so here is 38. The presentation is not 38. 38 is this extra. Yes, and we have this story, and this is actually what we want to understand theoretically, kind of what is it true or not true? Because those who study transport equation tells to us, guys, but okay, you have diffusion, that's okay, this is a transition, but without diffusion there should be only 0 and 1, yes? And you kind of pretend that you have a visible part of your domain, certain intermediate concentration. I mean, guys, are you sure? Yes, and we are not sure. Well, so this is why we continue our research. And now I come more to theoretical part. So it's kind of end of numerical, end of petroleum and numerical part. Now it starts theoretical. So this now I need to consider a simpler problem. So I still have a porous media, but now it's I have movement not from the left to the right, but from up to down, and this is just a gravitation. No viscosity anymore, but I have two miscible liquids. One is heavy and one is light. And heavy is on top, light is on bottom, and I have gravitation. And yes, we have, they want to interchange, but they cannot do it in a stable way, and there is a toy for kids, yes, when you have two liquids, and they change, and it's very beautiful, and the kids are happy, yes? So basically, the model of this toy, but in the toy it's not a porous media. Yes? So I assume that here it is a porous media, and if you look to equations, So the transport equations is identically the same. I don't know why I didn't write it in an identical manner. Yes. Uncompressibility condition is exactly the same. The law is slightly different because I don't have diffusion. I have just velocities just proportional to gradient, but I have a gravitational correction here. Yeah, so this is the equations. And also I'm a mathematician. C loses idea of concentration. Now C becomes from -1 to 1 to have certain symmetry. So heavy is +1, light is -1. Yes, and okay, this is once again those equations, and this is called incompressible porous media equation. And okay, we have miscible displacement, so we have diffusion. 1 minute of not related to the talk, but much more popular is the problem when epsilon is equal to 0, when you don't have diffusion. This is actually incompressible porous media. And then if it is incompressible porous media, it is a part of the general story of studying Navier-Stokes, Euler, Muscat problems, existence, uniqueness of solution, formation of blow-up, construction of via convex, non-uniqueness via convex integration. Okay, blow-up is still an open question, actually. Yes, so I here write blow-up, but it's blow-up in infinite time, yes, so which is not really a blow up. Actually, it happens that even if you consider small perturbation of a stable state, light liquid on top, heavy liquid on bottom, it's still not very easy. Yes, so it's still not completely open problem, but I'm still interested in the problem which is important for petroleum engineering. So not just question, not just, unfortunately, not the questions of regularity which would make us closer to Navier-Stokes, but just a question of what is the, okay, the dynamics also forms such type of fingers. What is the speed of those fingers? And okay, once again, Otto Menon, actually they started with not viscous problem, but with this one. And for the full model, they can prove that the velocity is less or equal than 2 of those fingers. But for this reduced model, transverse flow equilibrium, you can repeat it. Yes, so repeat the same idea. They proved that it is less than 1. And this is a question: is it a sharp estimate or not? Numerics, experiments, and the others contradicts to each other. So you read the literature, you will find papers which says that yes, it is 1, and you will say that no, it is completely far from 1. I'm sorry. When you work with petroleum, you always have this story. Right? They don't have annals of petroleum engineering where the final answer is given. Yes. Here I cite my favorite work here. So it was a simulation of this with a specially designed method, pseudo-spectral method. And if someone here is interested in quantum computing, I'm very interested to repeat this method in quantum computers. But what it shows that if you look onto this problem as a 2D problem, the velocity is 0.84, and I would never say numerical 0.84 is equal to theoretical 1 or not. Sorry, yes, so that's, but in dimension 3 they showed it 0.6, and I mean this is far enough, yes, from 1. So we believe that there is a room for improvement. We don't know what is this room. And okay, I would be happy, I would dream to have a next slide. Oh, we did this. No, we didn't. But we did the further simplification, which in a certain sense, which makes certain sense. So okay, here I didn't manage to draw a super good graphic, but idea is the following. The finger is almost vertical. Let us assume that it is vertical. And finger, and let us put it inside the tube and assume that in this tube the movement is one-dimensional, the dynamics is one-dimensional. And we have several tubes and we allow cross flow between the tubes. Yeah, so kind of all the mechanisms which we expect to be important are there. Of course, we made discretization. Yes, of course, it's not the original model. Yeah, so that's. But what is also interesting here that if you compare it with numerical schemes, because numerical schemes do some discretization with a certain grid, and if you consider a specific form of grid where kind of your discretization is horizontal direction is fixed and your vertical direction is as tiny as you can, then okay, you write equations for this numerical scheme and you assume that this step of the discretization converges to 0, you will get in the limit some system of equations, and this would be exactly the same system of equations which is on the next slide, which we study. And for concreteness, it corresponds to finite volume upwind method, which is used for such type of problems. So this is not an invention. Yes, so let us, I would present a model only for simplest case, 2 tubes, and give to you your imagination for n tubes how to write it. Yeah, so assume that we have 2 tubes. Then in each of the tube we have concentration, velocity of the liquid, and pressure. So nothing changed. But we also have a cross flow between the tubes, and we will call it intensity of the flux, intensity of transverse flux. And here we can start to write, you know, equation by equation. So we had the transport equation, then it's here inside the tube, you know, it is just a copy of it effectively, but there is a cross flow between them. And cross flow I denoted by letter B, and it is proportional to intensity, and here comes not very important detail, but it affects the proofs, because in the end there would be theorems, and it is pain for the proving theorems, is that it's proportional to intensity, and it also should choose the concentration which it is used. And if you have a if your flux is from first to the second, then you are multiplied by C1, and if it is from second to the first, it is multiplied for C2. Luckily, the transition happens when intensity is equal to 0, so it is continuous and moreover Lipschitz function, but it is not differentiable. And because in the end, in the core of the proofs would be dynamical systems, there would be smooth dynamical system. And smooth dynamical system for not differentiable systems is not very well. Yes, so this would later. Okay, we would have some theorems, and you can ask why you don't have more theorems, and this is the answer. Yes, the most different part happens in Darcy law. Once again, inside the tube, you just copy the equation of Darcy law, but you have intensity of the flux. And then you don't have a gradient of pressure in horizontal direction. Yes, you need to consider difference of pressures and divide by the distance. So you actually need to introduce the distance between those tubes as a new parameter. And let me admit why you should divide not by L, but by L squared. But mathematically it doesn't matter, because this is still one free parameter. But from physical point of view, L squared is much better constant. It's intensity, not as velocity. Yes, and incompressibility condition is very simple. It's just copy of this one. Okay, this is the system, and I copy it, and what is happening here? If you do numerics of this, you observe, and now that's how to say, this was 2 vertical tubes, yes, and coordinate there was y. Now when we draw, this coordinate becomes horizontal. I'm very sorry. Yes, that what is happening here? So the blue line is the concentration in one tube, and the green line is the concentration in other tube. And it forms 2 traveling waves. One propagates to the right, which means to the top, and one propagates to the left, which means to the bottom. And what is more important, they form that it doesn't go from -1 to 1 directly. It goes from -1 to 2 intermediate values, and from those intermediate values to 1, 1. And this is, we think, is a kind of manifestation of this intermediate concentration. Because if you draw these two tubes, you recall that they were tubes actually, yes, then you will see the following. Yes, so that's, you will have here +1, +1, -1, -1. Here would be C1 star, here would be C2 star, and the tiny transition layers here. Yes, and you will see, so C1 is say almost -1/2, and C2 is almost +1/2, and in that case you can think that this is one finger, and this is another finger. Yeah, so if you look on this as a picture, this is a manifestation of fingering, manifestation of intermediate concentration at the same time. And actually, it's not just a numerical observation, it is a theorem. So here, okay, it's a theorem only for sufficiently small value of L, the distance between tubes. So then we have two values such that you have a traveling wave from -1, -1 to those two values, and from those two values to 1, 1. We don't know exact values of this C1 and C2, but we can prove that they are separated from ±1. We can find their limits when L converges to 0, and this is -1/2 and +1/2. So I don't think that in true system I have -1/2 and +1/2. Yes, because okay, this is two tubes. I mean, this is oversimplification, but still this could be considered as a mechanism. Yes, as a manifestation of the mechanism. And as I told, I would like to speak about my expertise, just to share with everybody what I can do. Yes, and strategy of the proof comes inside dynamical systems. So up to now, there was a petroleum engineering numerical simulation. I formulated problem which is basically PDE or fluid dynamics is not clear, yes, because those equations is correctly to consider reaction diffusion equations. They're less fluid equations, they are more reaction diffusion type. But now it comes dynamical systems. Because when we want to do a traveling wave, and what is the traveling wave is that when it doesn't depend just on x and t, it actually depends on x minus vt. Yes, for some speed. And then you can make a substitution into these wonderful equations, and you will get a dynamical system. And it would be a dynamical system, 6-dimensional dynamical system, because each concentration enters as two variables, because we have here second derivative, and the rest, it happens that it actually doesn't depend on pressures, it depends only on the difference of pressures, and two velocities, they sum up to 0 because of the conservation law. So kind of it, from 4 other variables, only 2 survives. But still it is 6-dimensional dynamical system. And what we are interested in is heteroclinic orbits. So the orbits which goes from, say, -1, -1 on one side to some other 2 points when this parameter psi goes to infinity. And it happens that if you study the set of equilibria of this system, it's a 2-dimensional plane. So those who love hyperbolic systems, disculpa, sorry, it's not hyperbolic because you have too many equilibria. And studying, I don't know, indexes of them, dimensions of stable, unstable manifolds, you come up with that the best chance which you can have is the following. So because here there was a parameter v. And then the best chance which you can have is that for every parameter v, you have a single value, C1, C2, to which you have a heteroclinic. But you don't know value of parameter v. Kind of you have a curve of possible values of C1, C2, where you can go with this backward traveling wave. Now you repeat the same idea for +1, +1, and you will get a curve here. And two curves in 2-dimensional plane in the best situation intersects in 1 point. And actually what we do, we prove that exactly this is happening. And on the next slide, I would like to open a bit why we have this small L assumption. In the proof that this is our system, and it happens that it is nicely separated to the concentration part, and we call it pressure velocity part, and L appears only on pressure velocity part. And after proper change of variable, which is basically rescaling, you get that the pressure part can be written in such form: L times derivative of this new rescaled variable is certain linear map multiplied by QU. And this is so-called singularly perturbed systems. And here I omit the details, and those who are fan of hyperbolic dynamics, which was my original subject of my PhD, and so that yes, this matrix which is here is hyperbolic, and then we can use singular perturbation theory, whatever you prefer, Fini-Shell or Hirsch-Bishop for normally hyperbolic systems. And then inside this 6-dimensional system, you can prove that there is an invariant 4-dimensional manifold, which is a normally hyperbolic manifold. And here it is what is unusual for this type of problems, that this is not attractor. So you have 1-dimensional direction which is unstable, so how you leave this manifold, a 1-dimensional direction which is stable, so it's really hyperbolic, which I have found not so typical for such type of system, but in the end it allows us to close up the story. And once again, this L conversion to 0, it's actually the same idea as was with this transverse flow equilibrium simplification. When I said the pressure mostly depends on horizontal, not on vertical. It's the same type of the passage to the limit. And then I just write this system. So it's once again now pressure depends on Y, yes, on vertical coordinate, not on X coordinate, but it would be the same. Instead of this C bar, now is just an average concentration along the horizontal line, actually much easier to understand. What goes further would be only about this system. Yeah, so I would dream to prove further results about that one as well, but now I'm not able. Yeah, so the theorem which I presented for 2 tubes was for both, and the reason why we have more results for this one, but we cannot extend them by the same strategy to the original one, is this not differentiability of the term which I told. Yeah, so it's not presented in the PDE part, but it is presented on every type of discretization which we would do later. Okay, I explained this on the 2 tubes, yes, and if your imagination works correctly with this idea how it could be generalized, it happens that it could be generalized not just to 2 tubes, 3 tubes, 4 tubes. It can be generalized to a graph of tubes. So you have several tubes in the space, they're vertical, and they are somehow connected to each. They have their widths, which would be represented by measure, and they are somehow connected to each other. Yes, the distance between them, what is the surface of tangency, all of those parameters. And then you can write the system and repeat everything with the same ideas which I wrote. Yes, and then this is the system of equations which you will get. So I'm not expecting, yes, Rodrigo correctly said, I'm not expecting you to read them actually, yes, so that's, but I would like just to show what type of equations it is. So it's still a reaction diffusion advection equation. So I still have transport equation on the left and still have some fluxes going out to other tubes there. I still have this if inside, so they're not differentiable. And okay, now that's I have certain equations how to write the transverse intensity. Okay. But now it happens that, okay, if we look onto the original problem and just try to discretize, then we will just get, okay, I assume that my was not a square, but it was a cylinder, yes. Then it is just corresponds to this notation to a cyclic graph. Yeah, so that's, and I can write the same system and I can do numerics of it. And for 3 tubes, I see that it would be 3 traveling waves. For 4 tubes, the system forms 4 traveling waves. Starting from further, it is not correct anymore. And starting from, say, 7, it's obviously not like this. Actually, to 5, you can still think, might be this is error of numerics. No. From 7, you clearly see that it is not like this, but still there is a certain elongation with the kind of, it's not exactly correct that it is n traveling waves, but it is not completely stupid idea to say this. And we want to understand up to like what a progress in this direction we can make. Interestingly, that these graph models allow us immediately to include multidimensional spaces because we have lattices, yes, and there were a lot of lattices in these conferences, yes, so, but okay, this is different one, there is no potential. So here it is different, at each point there is a differential equation, but who knows, yes. And moreover, it could be generalized to what is called graphon. Yes, when you have as a set of vertices of your graph, not finite number of points, but you have a measurable space. Yes, and each point of the space is kind of a tube, and they still would be connected. Yes, so you still can have edges between points. This becomes a function of 2 variables. Yes, and then we can go, we define concentration, velocity, flux. I mean, I just once again wrote it here. It happens that it becomes here differential and here integral. So it becomes differential integral equation after this. But all the differential is in variable y, vertical coordinate, and all integration are with respect to this measure, which represents graphon. Yes, and okay, this equation, those equations make sense. And the good and not good story is that the proper spaces here are L infinity, and they are L infinity because I need to consider here product. Yes, and I need to consider product and stay in the same space. It actually kind of almost forces us to be L infinity. Yes, but the good story that if you write all of this down here in a short notation, this is a standard notation of semigroups, and the solution can be defined in terms of semigroups, or in terms of semigroups from acting on bounded uniformly continuous functions. And integral should be defined as a Bochner integral, but I mean, on all this way, the difficulty not really appears. Yes, it's just okay, but it could be done via classical ways. Up to now, we have only local solution. I expect that we would manage to prove global as well. So this part, the graphon part, is a work in progress. Yes. Now, okay, a special type of graphon is graph. And here we have some graphs for which we have a good description. And this is full graphs. So assume that you have finite number of tubes and they are pairwise connected. Everybody is connected to everybody. Then we can prove that there exists a family, the cascade of traveling waves for n tubes, n traveling waves. And this is, okay, if you recall that this is tubes, this is how it would look like the form. you can say that this is just two fingers under proper imagination. Yes, and also intermediate concentration is there. Yes. Okay, this is a theorem. Another theorem that if your measurable space is really graphon and it is rich enough, basically it is infinite, yes, then you can construct a infinite cascade of traveling waves. Here we do, like in all the cases, we don't know if it is stable or not stable. For this one, we did numerics and we observe it as a stable one. Infinite could not be stable in a certain sense because there are close to each other cascades. Yes, infinite cascades. But still, we hope that it could be observable. So that's, I have found this is an intriguing construction of just infinite cascade of traveling waves. And there as well, we have intermediate concentration. It would be 0. And okay, now the presentation of the results finished, but there is how to say, directions of further work. Oh, it is finished. No, okay, nice, yes. Yeah, if I find oil. So the further direction, so theoretical, yes. So actually what I would like to do is to find a formal connection between this Pisman model and this simplified model for real two-dimensional equation. What we actually doing, yes, because there was this passage L converges to 0 inside, yes, so this type of stuff. If you try to recover this into PD setting, it would be the following. So first of all, so about diffusion, survives only vertical diffusion. We actually, in all our models, we removed horizontal diffusion. And this makes us closer to this incompressible porous media equation with 0 diffusion, yes? So kind of we are closer to the Navier-Stokes, yes? Even that we are still very far, but one step closer. Another thing that actually parameter L doesn't exist in original setting. What exists how it can be introduced, you should assume that permeability in horizontal and vertical direction, that they are different. In the Darcy law, you need to put in front of gradient of pressure a tensor. Yes, which, okay, it's diagonal and it has 2 coefficients, and you need to consider proper limit of ratio of those coefficients to 0, and then you get this transversal equilibrium model, for which actually, for discretization of which there was this fancy results with graphon. And the question in which sense they can be close. I born in dynamical systems world. I believe that PDU world has their own naming for this, which I'm not really familiar. But because both problems are highly unstable, so you cannot expect that with the same initial data, the solutions would be close to each other. But what you can hope for is in dynamical systems so-called shadowing style, which tells that for any solution of this system, there exists a solution of this system which is closed, but might be with a different initial data. It could be considered as you can let us consider space of set of solutions that one lies in the neighborhood of another one. Yes, it can be, I don't know, it should be called kind of stability of the space of solutions, something like this. This is very similar concept. And I don't formulate this as a conjecture because I still need to say in which norms, I don't know, and other. And another thing which I would like to say that I cannot be sure that this is correct, and I cannot be sure that the next thing which I am speaking is correct. But if you look, now I do this model and I did a lot of numerics of it, and I tried my best, and I had to study how to use graphic cards, yes, to be able to do this better. But what I observe, so when I do simulation for a small time, I mean not small but average, moderate time, yes, then yes, I observe the fingers as we expect, which are chaotic, fluctuating, unpredictable. But when I do numerics for a very, very, very long time, and T is proportional, L is kind of number of elements of discretization, and here T is proportional to L, and here T is proportional to L squared. And L squared comes not from nothing, it comes from energetic estimate from Felix Otto, kind of that they suggest that there should be different regimes, actually. And it happens that this is different regimes, because what I observe numerically is that I have just one finger going looking to the top and one finger going to the bottom, and what is surprised, they're not necessarily looking like on this picture, yes, so they can be shifted to each other, and in between there is a certain zone which I don't know how to explain. And what is interesting here, I can theoretically predict this part. Yes, for example, there is a profile here, and I can theoretically calculate it. Yes, so what it is there. And the same is here, but I don't know what is the zone here. And remember my question about n-tubes and n-traveling waves. Who knows, might be for n, it is very complicated problem, but for infinity, I have it, because from this picture, it is just 3 zones. Here, there is a traveling wave, here, constant state, and one more zone, okay, which I don't know how to explain now, but who knows, you know, there is a time for research. And I would like to end with a coming back to the origin of the talk, yes, because I enjoyed very much that the statements of the problem which I study here comes actually from practical problems from petroleum companies. So we had a petroleum company nearby, yes, and all this finger story, of course they were not interested in graphons, in traveling waves, yes, but we were doing with them some other stuff, yes, related. And okay, it was done in Russian context, where the most promising enhanced oil recovery methods was chemical. But a very similar effects appears and when you do thermal or gas injection. Actually, if you come to the story of the Pisman model, so for me, Pisman model was for water inside polymer. Original equations was gas inside oil. Yeah, so that's, and in Brazil, actually, gas, because what type of the techniques you use depends on the oil field. Yes, it's not from mathematicians. Yes, it's from oil fields and equipment which is already developed or not developed. Yes, and so here it is gas injection, because actually there are a lot of gas inside oil fields, and actually it is kind of produced and you want to re-inject it. Yes, and then water alternating gas, because when you just inject gas, all these crazy pictures which I showed up appears and you doesn't want them. And one of the techniques is water alternating gas. And what is happening inside, like if you start to look the mechanism why water alternating gas works, it's almost kind of increasing viscosity of the water. Yeah, so it's polymer basically. And another thing, so I also have some research on hysteresis. So for water alternating gas, hysteresis appears. But what I'm the most excited that this is what I learned only after I came to Brazil. So in Brazil, there is a popular thing, acidizing. This is a completely different story. You inject some chemicals, acids, which doesn't move liquids, but they affect porous media. So they interact with porous media. And there they also have fingers. So this is picture of simulation of acidizing, quite similar to what I had. But this is not viscous or gravitational, this is chemical finger. So here there is a chemical reaction happening, not displacement. But what is good that for acidizing, they actually won't have fingers. So in all my talk, the fingers was an enemy. I was fighting against them. No, here it is your friend. So thank you very much for your attention.
Oh, okay, so questions or comments to Sergey? Okay.
So let me see if I understood something correctly. When you first showed like the graph model for the different tubes interacting, there was like a problem after the next picture maybe. When you had like more than 7 tubes, it started not to look so much like 7 traveling waves, right?
It's not anymore 7 traveling waves.
But
yes.
when you did the graphon one and you had like, it looked like you had n traveling waves for n tubes, right?
Yes.
So what's happening there? Why
What is
it
the
different?
graph, underlying graph? Here we have a cyclic graph, so only neighbor interaction. And for this n tubes or graphon style, we have all-to-all interaction. So this is the difference. We would actually kind of the story is that we would dream to prove it for this one, and we were experimenting around, yes, and we have realized, because there inside you have some matrices, blah blah blah, and if those matrices commutes, we can do, yes, and it happens that they commute for 2 tubes, they commute for 3 tubes, but it doesn't commute for 4 tubes. Yes, and we started to investigate this phenomenon, and we realized that they commute for the full graph. Yes, this is what's because inside it is. I didn't include, but this is conservation laws basically, like when you try to find them. Conservation laws in non-divergent form.
Okay, thank you.
Is it an answer to your question?
Thank you.
Okay, yeah.
More questions or comments for Sergey? No, just a comment that it's very nice that you are here, because one of the nice things that we do in this conference is bring different people from outside and from inside, that you are able to mix theoretical with numerics, right? Which in Brazil is not.
And with industry.
Yeah, exactly. And which is in Brazil is not exactly the case. Here we have this kind of you do simulations, and you are far from the theoretical part, and sometimes the positive. But it's very nice that you are able to combine both. Okay, let's thank Sergey again. he's my PhD student, and he's Felipe Monteveller, he's my master student. And as we realized during the week, a lot of people they were very happy that we are recording the talks. So what happened that probably most of you realized that we had some kind of good luck and bad luck in the same time, because there was a lot of conference here in the same time, and so at some moment we were without support to record. So so then we decided to go further and do anyway, and so we did ourselves. So that's why I ask for our cameramen. So thank you. So a lot of people do, but they were one of the main that they were responsible for the record the talks, also the coffee breaks, and also for my wife that he managed to get the coffee breaks for this week. she was responsible. So Pita, we are recording. Thank you. Okay, so so she works at in another university, and so muito obrigado, Pita. E agora, okay. So in the beginning, I was not one of the speakers, but some of the speakers gave up. Others appears, and in the end, I decide to give this talk. It will be more or less a more historical talk than the technical talk, and maybe Sergey stole the. No, he's not. Okay, Sergey, sorry, you didn't stole. So this what do I do? Okay, since he is recording, I will discuss more or less the history of this problem, some of the collaborators and the responsibles for what we proved. They are here in the room, and it was more or less some kind of the history of how the things are happening, and how we achieve some results in this line of investigation. So the papers, most of them were supported by FAPESP. And okay, I am supported by CNPq grant, and so okay, so this is the picture from yesterday. Everybody here is okay. We have Aldo here. It's my advisor, also Arnaud, because we have a student together. It was Ariana we mentioned, and the rest of these people a lot of interaction between them. We wrote a lot of papers, and they were the responsible for the papers, and they are writing other papers. And so we have undergraduate studies also that they are here, also Luisa, and this is one thing that I let's say. I realized that was very, let's say, at some moment in my career, it was very, very bad to be alone. So what I did, I put a lot of effort to avoid this, and I have feedback from the students also. They prefer to work together. So I will discuss all the talk is about the King fields, but just to mention that we had. Several PhD theses, which or the main result of the thesis are about some model with the K field, or one of the results of the thesis are about the K field. This it was a student of it's Roberto Villa. It's a student from Leandro and from Shang that I will mention during the talk, but essentially he glue the uniqueness. When the fields decay slowly, we have a proof with Presucci and Marcio, and Leandro also that we have unicity at low temperatures, and by Dobrushin we have uniqueness by high temperature, and it was some kind of gap. So he managed to glue the gap. And Eric, which was a cotutela project with Arnaud, which is here, and also we work in the tree for the K field also, and we have a paper also in the first paper actually in the long range 1D. It was with Eric and with Bruno, which he also is here in the room. So Eric has a paper on this thesis, has a paper about the K fields on the tree, and Bruno, one of the papers of his thesis. Actually, Bruno was my master student, but he did PhD with Violeta Russell, which was a student of Arnaud, which is here. That also he got one of the results of this about the K fields. And after I continued this, let's say, doing some kind of changing the model, changing the so we have more 3 PhD theses. The last one was on Wednesday about models with when you have the K field. So I will try to explain why it's so. Let's say why we did this. At some moment, Abel Klein said, oh, Rodrigo, why you are doing this? So I will try to convince you to which is nice. And so okay. By the way, this thesis received the cum laude in Netherlands, which is a very nice experience for us for a Brazilian student. That's very nice. They prepare both a diploma, and then if you fail it, you get one. If you are successful, you get another one. So this is what it was very, and they have a different style of PhD defense in Netherlands. I strongly suggest to try to do a cotutela with Netherlands. Okay, so I will not able to, because this more or less was said during the week. I will try to stay here, and I will stop in the midday, and doesn't matter where I am. So okay. So during this week we saw several times the Ising model. Unfortunately, I'm still stuck in ferromagnetic case. Maybe in the future you have maybe another students, and so is ferromagnetic. And the main issue here that we will work with this kind of the behavior of the field. Will more or less say to me what will be the results according to the K of the K of the field. So the intuition is very easy actually. I will record mainly for the students that we have this result that when the field is uniform and different from zero, you have uniqueness, and when you have zero field, you have phase transition. So the idea is that if the field decay fast, you simulate zero field. If the field decays slowly, you simulate the uniform and non-null field. This should be, if you think about it, should be what should happen. As Marcio Cassandro said, if there is any justice in the world, should be like that. So that's what we try to prove in most of the papers. But one thing that's important here that make a lot of the proofs, you have to get some idea at some moment, which is the model became, which is that the interaction is not translation invariant anymore. So you are outside of error theory. You have to have new ideas. Basically, one of the, and okay, I will explain more. But basically, I will describe some results for the nearest neighbors. That where we started, and now in this week, in the last, let's say, 5 years, we were concentrate here. So okay, why this is nice? So okay, consider the pressure of free energy. Let's say let's assume as Simon don't care about if you have a beta or not. This is really don't matter. This is a finite pressure at finite volume, and you can take the limits. And since the graph is amenable, means this one, doesn't matter what boundary condition you put here. So the pressure function, as the graph is amenable, you don't the pressure does not see the boundary condition. This is you see in your first course of physical mechanics, and. But what happens that you can prove these equalities, about the derivatives with respect to the field. Suppose that the field is uniform for a moment, and for any age you have this equality. And then, if using correlation equalities, if you have the equality of the derivatives, you have the equality of these measures, and use some kind of standard correlation equalities, and you have uniqueness. So, if you have the derivative with respect to the field, you have the uniqueness of the measure. This is one of the things that you learn. And you can use also complex variables. You can consider complex random fields. And this is a very old result that everybody from physical mechanics knows, that if the field is uniform and not zero, you have uniqueness of the Gibbs measure for any temperature. This was, let's say, in 2010, this was a very problematic situation for us, for me and for Leandro, when we started the project, because we would try to discuss with the people from the physics department. We have friends there, and we said that let's say the following. Okay, I have an Ising model, and with a positive magnetic field in every side, and you have a transition. So immediately you start a fight. And now we have a literature, but at this moment, people were confused, nobody believed us, and our first pulse was wrong, so it's a very, very bad, tremendously bad situation for us. We were students, nobody believed us, and this was the situation in 2010, more or less, because of this. The thing is, I'm assuming that the age is uniform. If you change, if the age, if the field depends of the space, of the position, the game is completely different. So that's why people were confused, because in general, when you say positive field, they interpreted, they thought that was uniform, but it's not the case. And then that was the question that we started with Leandro in 2007, no, 8 maybe, and try to study this problem. Okay, I will do this calculation because it's very easy. And let's just define what is the case to zero, which means that let's suppose that we have only non-negative fields. And the case to zero is like that. You for any epsilon that you give me, at some moment when you are far from the origin, you are below this epsilon. This is a fair definition for the k into zero. And with this definition, you can prove, I will show the calculation in the next slide, that doesn't matter the speed, doesn't matter anything of the field, just the case to zero. The pressure is the same pressure of the zero field. So you cannot, let's say, sometimes you are in dynamical systems that you say that you have a phase transition when the pressure is a point which is not analytic, but this is not, you cannot do this for this class of models, and because the pressure is the same of the pressure with zero field. So you have to use another strategy to see a difference for the Gibbs states for the model, basically because you are not translation invariant anymore, and the usual standard arguments does not work. You cannot use the pressure, as you will see, since the pressure is zero. For example, in dimension 2, the pressure from Zagreb, for example, are included here. So you have a point when the pressure is not analytic, but if for the field that the case is lowly, you have one unique Gibbs measure for every beta, even if you have a point when the pressure is not analytic. That's why it's some kind of nice problem that you have to, I mean, you have the original pressure, but the set of Gibbs measure are they are running, they are changing according to the decay of the field. This was, let's say, the motivation. A lot of people, after realize it, they start to agree that maybe this is a nice problem also, because you have to go by other side. You cannot use the standard pressure results. You have to do directly with the measure. And this is the proof that I was in a conference and the guy said that they don't believe that is possible, but exactly this. The thing that when you do the partition function is some kind of log. You can so it's in the integral of exponent of something. You have some. And you here you put the different bound, but you have a difference of numbers like this, and because that the log of the partition function, the log of the integral, you can prove this. You can prove this inequality here because of the pressure is like that. You can prove this inequality, and then it's more or less easy because the field will cancellate, the field 0 field with 1. Here you take the sup norm, and this is very easy calculation. You have this inequality. You see, it's really easy. And then you have to divide by the volume because you are calculate the pressure. And since your field is decaying to 0, and some moment you have a box large enough, you can given an epsilon, you can get a box large enough. You have this, and this part goes to 0 also because you have your graph is amenable. This is the proof. Sorry. Yeah, no, I mean, the a priori measure is the same, right? Yes, I mean, here you have the a priori measure. Yes, it's the same. No, but because when you integrate, you have to, in your Hamiltonian, you have your let's say, you have your boundary condition, you see. Yes, it's like, yeah, okay. So it's like, but the a priori measure is the same. So, so this is the proof that you can believe me that the K fields, they don't see the pressure. The pressure is the same pressure of the pressure with 0 field. So this was my first paper of my career, and was published in 1st April. Which why? Because nobody believed in this result. Everybody make jokes, and Leandro was my colleague in the Federal University of Minas Gerais, and here I will let's say here will be historical part now. So the question is like that. I will tell about this moment. I think mainly for the students. So I was in the ergo-theory, so I was not happy that people don't know nothing about the models. They say very vaguely things about the models. I didn't like this, so I jumped, and so I went to go to Minas Gerais to do the PG with Aldo, which is here also. And then, when I arrived in Minas Gerais, Aldo immediately went to France. So he was there, and he met Roberto Fernandes after he became my co-advisor. So so Aldo was there, and I was in Minas Gerais. So we are so during this period that sometimes is sometimes if you are alone is bad, but it's also good because you have to react in some sense. So we start to do discussions with Leandro about what do if you know this, know another thing, and we have this discussion about fields that we were not uniform, and we didn't manage to prove nothing, and when Aldo come back. We were in some kind of international conference of mathematical physics. I think Vladas organized it. So Aldo presented me Roberto. Here is Roberto. You will go with him. So it's very good and very bad because I didn't know French. So I have to run to learn French. And in the end I managed in some way to learn a couple of some French, and I was in I was in Wuhan for 6 months. And when I arrived in Wuhan, I asked to Roberto about the fields and what you think. So he really didn't understand in the beginning, but he thought that I was trying to learn about Li-Young theorem, which is essential for the uniform field. So he gave me a lot of papers, and gave these papers, and okay. So I was trying to read something or not, but none of these papers has, because in the physics literature is a lot of uniform things, and less literature about the fields which is more general. And then nothing was working. But I was a student of Auto, and I was aware about this Fernandes-Procat criteria. And there I met Giulio Cobelli, which was a student of Arnaud. And Giulio was trying very hard to read the proof of Fernandes-Procat, and he didn't get it. It's very difficult. So okay, Giulio, I am a student of Aldo. I have some calculations that Aldo shared with me. I can. So I helped Giulio with, because I have some literature and some calculation with more or less more open than in the article. And Giulio was very grateful. Giulio, thanks a lot, Rodrigo. And then you give me some material, so I will give you a paper. So he passed to me a paper from Charles Pfister, from large aviation, right? And this paper, the field is totally. He does cluster expansion, and he does large aviation and so on, but he writes the thing in at least part of the paper for the field totally general. So we got this paper basically by chance, because I helped Giulio, and Giulio said, I have to return you're very nice, so get this paper. And the paper is precisely what I need. So we use this, we start in this paper by Pfister, and we wrote this proof. Actually, I erased it, but to be honest, we did the Pile's argument, but actually after we discovered that this result, we did by hands using Pile's argument and so on, but by an abstract of theorem from Georg's book, actually it was already known, because by finite energy perturbations you cannot change the phase diagram. So it was nice that the people allow us to publish, but actually by abstract results is already known. But it was nice because it was the beginning. And then Maria Eulalia invited Enrico Presutti for a Brazilian School of Probability, and I told him about this problem, and he thought very nice. We started to work together, and after I visited him in L'Aquila, he passed away, as Pierre mentioned already. But then this started basically a new line of investigation. But in the beginning it was very bad, even because maybe the last thing that I will say about this thing, when we finally managed to have a manuscript, we were very excited, but very afraid. Is maybe I remember that I wrote to Roberto that we have this, and Roberto said, it's very. I'm a bit surprised, but I don't see anything that contradicts this statement. So do the following: write to Arnaud, which I didn't know at this moment, and ask him what he thinks, and put me in copy in the messaging, and let's see what he will say about this. So and Arnaud said, okay, very strange. Okay, is a first reaction. Let me think. And we exchanged a lot of messages, and then more or less started our collaboration. Thanks to Roberto, that he was not so. It was very new, let's say, to deal with things that were not translation invariant, let's say. So Roberto helped us and put me in contact with Arnaud, And so Arnaud had a lot of a big vision of that, and he helped us. But even so, the first proof was wrong. And then I asked help to Sasha Friedli to look a little bit of the manuscript. And Sasha, he said, okay, very nice, but are you sure that nobody did this? I'm completely sure. I searched the entire internet, nobody does. So he said, okay, go out of this room and put in your archive right now. Run, put in archive now. So okay, I run, we put in archive, we are very happy. This was in the morning, and in the night, Sasha sent a message saying the following: Rodrigo, I'm so sorry. You have a big mistake in your paper. The mistake is like that. It was a very silly mistake, contour inside of contour. You please, sorry, I didn't see in the beginning, but your paper is wrong. So we were completely broken. We get out. We erased the paper from archive, and after a couple of months, we were able to fix, at least for L1. This was the first version, which is easy, but we fix it and we publish. But just say to the students that, okay, maybe the beginning is very bad sometimes. so it took I don't know, 3 years maybe, or several wrong proofs until they get, which is not really a result, because by abstract arguments you can achieve the same, even a stronger thing. Okay, so this was the history, and but after this, I was going in confidence to advertise the problem. So I met Enrico Presucci, I met a lot of people, Arnaud, and so we produced a lot of literature about this kind of field. This is for the first one, 1st April, because it was wrong also, but now he's right. And with the exponents, with Marcio, this is the guy that a student of Leandro, which glued the uniqueness for the fields that came slowly. With Arnaud, we wrote a paper on the tree. We start to this project to erase the first neighbor interaction to be large enough. The Bruno was one of the main responsible. We did this, and finally, after I don't know, 8 years, we managed to prove some kind of much more, 15 years. We started 2010. So, and then we came up with this long-range result that was accepted in GEMS. But this is just saying that sometimes you have to do a long path if you want to do, let's say, difficult things. And now we have a lot of preprints that we more or less we extend out the things to the long-range part of the theory. And just to say about the exponents, this was the first, let's say, non-trivial result. And since we are using contours, we have to ask beta large enough. That was the first, let's say, strange thing, that we have uniqueness in low temperature, uniqueness in high temperature. At the end, the student of Leandro, he managed to glue, but in the paper we have this. And in these problems, you always have some kind of critical exponent for the field. In this case, is 1. And then, in general, what you do, if you ask for this H star very small, you are able to prove the phase transition also. We have the suspicion that maybe if you, okay, since you have to ask for a small H star to be phase transition, maybe if you have a very large H star, maybe you have uniqueness. Vladas was trying to prove this but after he died. And but he was very exciting about this exponent, that maybe to see both behaviors and the same exponent. He was, okay, you can ask for Eric because he was in touch with him when they were discussing this problem, but nobody knows how to do until now. And okay, this is the thesis of the Roberto Villa, which glued the uniqueness. And now is the flavor of the proofs. And the proofs basically is Pio's argument, but you always have this kind of stuff. You have some kind of contribution of the field, with some of the field in the region, against the the interaction with the boundary. Here is a kind of positive field, and the interaction with some negative boundary condition. And when you have long range, of course, you have, in addition to these connections, you have the connection with the entire lattice, but weaker and weaker when you are far and far. So all the arguments, at some moment you have to deal with this battle between the contribution of the field against the interaction between the region and the exterior of the box. And this was more or less mentioned in the talks during the week, but we discovered this paper of Tikhomirov as well, and they didn't do the cluster expansion, but they do the pious argument, and they use plackets. So this is more or less, and the plackets are connected, and more or less are the contours that you expect in multidimensional case. You have some rules and so on, but what happens that if you are okay, the message is the following: if you are long range, the connected, forget connectedness. It is more or less clear. You will see more in the next slides, and also is some extension of Pirogov-Sunai, but they have to ask very. Then we will try to push this with Kelvin now. And this was, I mentioned to Aldo in the talk of, I think Kelvin. Yes, and you see, this is this quantity. This quantity is the interaction between the finite region and the outside. And when you assume that the standard interaction for the long-range Ising models, for example, okay, this is a ball. What we do in the paper is to estimate these quantities for more complex regions. But for the balls, you can see that exactly you have 3 regimes in these models. You see, so the physicists, they know this a lot of time already. They don't know the proofs, but you find this in the literature of the physics, and you see, and now you can see why. More or less, plackets works for alpha is bigger than 3 + 1 because the surface term, the interaction is according to you have contribution as a surface, really, as and then you have to this more or less is a very strong indication that you cannot use plackets for the rest of the exponents. You see, when you arrive here, you more or less you have to. I mean, if you continue trying to use plackets, sure we will fail you. And in GEMS, finally we managed to prove. Okay, one thing that you can do is more or less like that. Let's say, since you have this, you have this estimate here, you can compare, for example, let's say the exponents. D minus delta with D minus 1, for example. Let's suppose that you want that the interaction win. So this guy should win this. So, okay, put bigger this guy. So the D cancel, and you have minus 1 bigger than minus delta. So change the sign, and you have this. You have above 1, you have Y, because the interaction wins from the field. So it's very natural to, okay, it took a long, a lot of years to draw this picture, but what happens that this is more or less, I learned to work with Arnaud, that you first thing that you do is some kind of qualitative, some arguments, and then you start to prove the things with, let's say, more sophisticated proofs. But this is more or less when you arrive here, you more or less you can guess the exponents, and that's why we did. And this is the part that I just mentioned. And okay, to be very, very, very honest, what happens that since you have phase transition for this region by the first neighbor interaction, this is not new really. because if you have the K-on field with the exponent with short range, you even increase the interaction. So of course you have this term is very strong in this triangle here. This is really the new part. And again, as before, if you ask the H star, actually depends of alpha, this H star, over the line you have phase ratio also. And this was part of the thesis of Lucas. And what happens at this moment, the group, and we did this, I don't know, several hundreds of meetings trying to learn as we can learn from Fermionic Systems. Every paper is very, very difficult. And the end, and this paper, the definition is not still the best one, because we are too much addicted in Fermionic Systems yet, and we use diameters, but diameter is not the best definition here. And so this is the more or less for the long range part are the let's say the inspiration, but we didn't start with this paper. We start with papers from Pico, and actually the first paper that we wrote, I read in Netherlands. It was by Cassandro Presutti, Merola, and Pablo Ferrari. It was in Journal of Mathematical Physics, and it was the first paper that I read, and after I read yours, and after read these papers, we entered in the Fermionic Systems. And which are here, these papers. And what happens in this moment that we realize that the papers that we were able to read at this moment, they use this hypothesis. And we start to work with Arnaud and also with Bruno, and to try to let's try to erase this. And we didn't manage in the first moment. And I was giving a talk in Rio de Janeiro to Eulalia's seminar. So Eulalia told me that she also tried to remove this with Enrico, actually, but she failed. So she said, I'm telling you because I gave up. So when I come back to our group, I wrote to Arnaud, I said, okay, Eulalia gave up, so let's try. So Bruno was able to let's say in the thesis of Bruno that I mentioned, that was Violeta student, he managed to erase this at least for an even smaller part of the exponents. And here start to this thing that I will construct with you at least once how to do with the multiscale analysis. But here start this thing that let's say when they are different when they are far apart. Here we are in dimension 1, so we use diameters. That we will see after we use volumes. But this is from Imber's papers. Okay, so you saw this picture with Kelvin. So you collect the incorrect points, which are these guys. And what is the game? The game is how to separate them when they are different, when they are the same object. And the thing is that they should be far apart according to some inequality similar to this one. And this is presenting out those papers of the scenes for Spencer, a lot of people. Sometimes they put some general exponent, but this is in all those papers they have this kind of stuff. So we want to let's say to say that they are different or not according some distance. Now in the 1D is diameter. That one of our contributions is exact change the diameter by the volume. It was João Maia in the thesis that we did this. And the thing that you saw in the Kelvin lecture, it was you consider the volume, which is full, the holes. So this is the volume of this region, and you consider now this inequality. So you say that they are different when they are the distance. Here you the volume that I just defined. And one thing that is very powerful in this multi-scale machinery that you have to do a lot of calculations to be able to work as we did. But one thing that's some kind of magical is that you can run a lot of part of the arguments and do not choose the M. Okay, the A you more or less have to more or less from the beginning you have to choose some clever way, A, but M you can is free. That's why it's so powerful. You can run with this M until very in the end of the argument you choose the M according to the exponent, dimension, and this kind of thing. Okay, this is a clever A to the calculation is not so ugly. And I will skip this because Kelvin already explained to you. But let me show how to works the multi-scale analysis. So first thing you tile the ZD. A very okay. A couple of comments. In For Expense and other papers, some of the papers they allow they can. Let's say they have some kind of a small intersection. It's true that works, but if you do like this, is for us it's much let's say safer. We were afraid in the beginning, but you tie to you have the let's say perfect tilings of ZD, and you do like that. So the next, let's say this is one scale, and the next one, you'll say the next scale is perfectly tiled by the previous one. This is one of the rules. And okay, this is exactly the coordinate of the cubes. And now, okay, I will explain with words, but the pictures will be much clearer. This M here will be R to some L, and L will be this K. So I will do two parameters R, and it will be after this parameter L will be L equal 1, 2, 2, and so on. And then to the arguments to work, one possible R should be something bigger than this guy, which A I choose it previously, and then I define the rules. So as I said, the cubes are defined that each next scale is perfectly tiled by the previous one. And then you have the sets of incorrect points. So you consider the cubes that intercept these regions. You saw here, what we will do, let's say, suppose that you have a strange figure with incorrect points. And then you put the scale, you tile perfectly the plan, and you pick up only the cubes which intersect these guys. Okay, do this, and then consider the minimal cover. Of course, that exists and is well defined because you have a perfect tiling of the cube. You see, it's much more safe and easily. You just tile completely the cube. So the cubes which intersect the region, you pick up. The rest you forget. And then you define some kind of graph of cubes. And okay, you will put an edge between the cubes when your cube satisfies this inequality. You see, so you have a lot of cubes, and you put some edges, and when the cubes they are close enough. And then in each step, now I will show to you how to do the multiscale analysis. You will collect the cubes. Okay, wait one moment. Oh, whoops. When you are here, since you put edges, you can discuss about connected components of cubes, because you said that the cubes are connected if they satisfy this. And then you imagine that you have some edges, and so now you have connected components of cubes. And what is the game? You will collect according to the scale. So you will collect the connected components which obeys this inequality. You remember your scale is L. So you are. I will show a picture right now. So you will run with L. So okay, so this A is the set of the incorrect points, and G is the graph of cubes that intercept. So you get on the volume. This is the volume of the let's say the cubes intersection with the incorrect point. This is the real volume. So you have some kind of bound for what you should extract in each scale according to these parameters. And let's see how it works in the real life. So okay, this is the collection of the incorrect points. So let's tally. So these are the cubes that that you touch the incorrect points. I pick up r equal 1, but it's very wrong because r should be bigger than the log of a, something like that. But that doesn't matter. They just run with the. Okay, I get this. So I use the rule of when the cubes are connected or not. So then I have this connected component. So because you see, remember, they have to obey this one. You see, they are connected if they obey this one. So if the distance is too big, they are not connected. So the connected components is this one is one. These two guys are connected component. The G3 is the big one, and this you have is one. So you have 4 connected components of cubes that you okay, is here actually, sorry. Okay. And these are the regions of the incorrect points according this, okay, in different connected component of the cubes. And what will you do? You will remove the regions because, okay, here is my L is 1. So I have 1 key behind, okay, 1 is invisible. For you multiply by 1, you don't see nothing. But okay, you have this. So remove all the regions that obey this bound. So okay, let's remove. Okay, you see? So I remove what? I remove this one and this one, which is smaller one. So you take, so this will you use to construct your first contours. And run again. Okay, now these guys. So okay, change the scale. Okay, now L equal 2. Now 2 you can see 2. So this is, okay, so take the connected components. And now they are too close, they are very close, so they are only one component. But okay, you put everything, but you have to remove what? What you have to remove only the regions that satisfies this bound. You see, okay, there are a lot of points that you don't satisfy. What you do? Again, run. And you do so on, since it's a finite region, at some moment you stopped. And now this is the last one. And you have your contours, which are these guys, 1 and 2 in the first scale, and the third one, which is gone. So what your contours? Your contours, remember, contours are this. They are not connected anymore. So your contours are what? This guy, this islands, small islands. This guy. So these two contours, they are different because they are far. You got from the third scale, and then you go and okay, scale, and then your next contour are these two, this Zielinski and this one, and they are your third contour. And then when you do let's say the proofs, you have to put labels according, okay, depends on what you want. Okay, for first transition, you can prove, for example, that the sign around in the boundary should be constant. This is a very easy exercise. And what happens is that if you do for the phase transition is enough to put the label only in the boundaries, and you have some kind of 2 in the power of the volume to control. But for the cluster expansion, in general, you put the configurations in the incorrect points. But this is just this. Actually, it's not so difficult as we mentioned in the beginning. But you have to keep in mind that you have this kind of let's say you have to collect the the objects according to the distance, and the distance, how much they should be apart. Far apart is let's say is for expensive, and this one it took 10 years to find exactly this definition. Even because actually, if it was not Pierre and Cassandra and these people, maybe more than 10, because we start with reading their papers. And I think that I will stop. I will just mention we prove a lot of things, but one thing that is like that. We prove the decay correlations, and João Maia, was a student that wrote the paper about random field. He said that they are able to extend the decay correlation till the critical beta in the beginning of the year. So I don't know if they managed, but they use different techniques using with random representations and things like that. And it's not exactly our result is not possible to up because we use the cluster expansion. And I will not mention any. I think. Okay, wait, not thank you yet. Just to mention one thing about the random field, which is a very, very famous model. This was by Ding in this paper, a new proof with respect to the Brickman-Copiani. But for us, we do the same strategy as Ding, but there you appear the volume of the interior with minus sign. But the proof essentially is the same, but what is the difficulty with respect to the Ding's paper? That we have to deal with sets which are not connected. So part of the proof essentially is you have to believe that your contours are not connected, but you should be able to finish the argument. And with these contours, they finish. Okay. Now we have the complete phase diagram for the random field because João finished the PhD with us, and he went to Peking, and they wrote this paper, which is exactly the complement of the Eisman results. So now we have the complete phase diagram for the random field Ising model. But we don't have the correlations that I asked you in the previous time, and we still don't have the decay correlation because, in Brickman-Copiani they proved that the decay is exponentially, but it's short range, right? So now we have, since we have the long range interaction, we don't know yet. So is this, and thank you very much for coming to the conference. Okay, you have some questions. Okay, now is I have maybe Thiago, you can yes, you can do this.
Thank you for your nice talk. So one short question. So this phase transitions business, that's one. But could you also say something about the deviations? So if you just try to look at the decay, the speed, this kind of entropy, this rate function, right, and which you characterize the speed of basically decay outside the support of maybe your limiting measures. If you think about this pressure, that's basically what is there written on the blackboard. That's easy. But if you look to the Gibbs state itself, and then try to characterize a large deviation principle for the sequence of Gibbs measures parameterized by lambda, basically. Is this known in this case, or is this some?
Okay, we have to ask to our know, but what the status is the following of this business here. If you have a proof for the standard contours, even if it's short range, but is, let's say, connected contours, you can try to get our contours, and if you check if the argument goes. Because in Ding paper, by the way, the Ding paper is very good. You can read. We check all. I mean, you can reproduce the proof, which is sometimes is a very difficult thing. And then what happens at some moment when you use contours, okay, is a big in the first moment you are a big afraid because you are not connected. Your entire life you play with balls. You are a very connected person in general. But what happens at some moment you manage to go further. So if you have a proof of this and use contours, what I'm saying that you can use our contours and see if the arguments goes. But I don't know if Arnaud has something to say about these deviations. You know that they.
Your deviations seem to have homogeneous, like you say that the probability of a volume deviation in the phase transition regime is like has a surface cost, and in a field you have first you basically estimate the probability in the wrong phase, and that you may change that a little bit if the field. I haven't thought about it now, but this is how I would start to think. And maybe I can say another comment that on the suggestion of Pierre, we were looking at the long-range model with random boundary conditions. The random boundary conditions, they kind of create a decaying field, but not of positive sign. It decays and it is random, so it's somehow in between the random field and the decaying field, so we're working on this. I wrote the first paper with Eric and Arnaud. So and there's a lot of people on the archive which takes too long to kind of rewrite, but anyway.
Okay. Yes. Most of the time we consider the positive field because some.
In some sense, all these things, like you say, your ball estimate is in a way like in the IMA argument. You look at the volume term versus a surface term, and due to the field, the kind of volume term is not like the volume, but like some power. And the question is the power larger or smaller than the surface?
Exactly.
So then you have a kind of feeling what should be true, and once you know what is true, you try to start proving.
Yeah, exactly. exactly. Exactly this. Okay. More questions or comments?
You show a paper by Ginibri
right.
About.
Wait, in the beginning.
Yes, in the beginning.
Oops.
Yes. Ginibri, Grossman, and Ruel. And you say that they work for in D dimension.
Yes, and they use the plackets.
And they use the usual contour, let's say.
Contour, yeah, contour argument, contour.
And you say that they do the Pies argument, but not the cluster expansion. In this, do you know if there is a paper that is doing cluster expansion for alpha greater than t+1 in the Ising model? I'm asking this because I wonder if the polymer expansion in this case would be with polymer that they interact not only with R-core interaction but also with long-range interaction.
I don't know if there is.
Okay, it's something that is typically not interesting for the physicists because they but maybe for someone that
you think you think I know that is really brilliant.
There may be a Russian paper. There was this big collection by the Russian and Sinai. I think one of the students may have done something like that.
Sinai student. Sinai student.
The student of the Russian Sinai.
No, maybe Sinai student. I don't remember his name.
Kerimov? No, Kerimov?
No.
No.
No, somebody else.
So Arnaud is he's bad in the Russians.
The Russian, but
I don't know.
you know the year, more or less.
It should be in the end of the 70s. There was a big correction.
But in English?
Yeah, that's right. My Russian is absent.
Okay.
Maybe it can be discovered by looking who is citing this paper. No?
Yes, exactly. But I remember that we were looking for if they in some moment they did the cluster expansion, and we didn't find this version. We didn't have this this comment of Arnaud. But yes, we don't know. Any more question or comment? So let's see you in the next conference.